So what I would like to talk about today is how we can merge traditional model-based methods, which we are accustomed to in signal and image processing, with deep learning in order to obtain efficient and interpretable methods in a variety of different applications. And in this talk here today, we're going to be looking at applications to imaging and in particular to medical imaging. So as we all know, in the past decade, really deep learning has revolutionized many fields with huge empirical success, particularly in areas where it was difficult to tackle using conventional optimization methods and areas where we have a lot of training data. So we could do all kinds of, crazy things. For example, we could spawn fake faces. We know that using deep learning, we could surpass human detection performance and classification performance. So there's many benefits, of course, we get from deep learning. But this, of course, also comes with a price. So we need very large training sets to get these good results. It could take very long to train these different networks. The networks are not necessarily interpretable, so it's very hard often to interpret the results. And sometimes there's a feeling that if you don't get the result you like, if you continue to kind of, brew, then you might end up getting a different result. The methods don't always generalize well. They're not necessarily very robust. And even when they are, often we end up with huge networks to get good performance. So for example, GPT-3, one of the famous successes, uses over 175 billion parameters. So this is, of course, a huge amount, which may not be relevant in medical applications. Now, on the other hand, if we look at signal processing or image processing that we're accustomed to more traditionally, these methods are heavily based on modeling. So we start with the model. The advantage is that we can very easily incorporate domain knowledge and structure into our problems and solutions. It typically allows inference from relatively small amounts of data. And also we could use analytical techniques to assess the quality of the output. So these are some of the advantages of more traditional methods. But of course, the big issue is that this relies on very accurate model knowledge, which in complicated problems we won't necessarily have. And also the inference could be quite slow. So in our work in recent years, and many other people, of course, have been working on this as well, we're looking at different techniques to kind of combine the advantages of model-based methods with the advantages of learning from data. So how could we do that? In order to see how we could do that intuitively without delving too deep into the math, let me try to give kind of a bird's eye view of what we do in model-based methods based on optimization and contrast that with what we do in standard deep learning methods. So in model-based methods, typically we'll have an input, which will be our measurement. Let's say this is a low resolution image, and we have a desired output, X. Let's say this is our high resolution image that we want to get. And we're going to have some known relationship that relates the two. So we know in advance, or we assume in advance, that our measurement Y is some function of X. Okay, so Y is approximately some G of X. And then in order to find our desired output X, we're going to define some metric. So it could be, for example, some sort of norm that we want to go ahead and minimize in order to find our solution. So we could use our favorite optimization algorithm to solve this problem. And typically, any optimization method we use will lead to something like this. We'll have some pre-processing. We'll then have some generic computation, and then a block that depends on our model, and we'll iterate on these blocks, and then we'll have some post-processing at the end. So this is what a standard optimization driven method would typically look like. Now, in the other hand, when we look at deep learning, of course, the situation is very different. So we'll start in trained network, in supervised networks, we'll start with many inputs and many paired outputs. We'll use them to train typically a fixed architecture. So the architecture is not necessarily tailored to our problem, but the weights are. So we'll use this to train the weights in a fixed architecture. And then when our new input comes in, we'll put it through this network and hope that, we'll get a good estimate of our output. So these are, of course, very different techniques. How could we merge them? So we've been looking at two methods that I'll describe briefly in the next few slides. So the first is deep unfolding or unrolling, where basically we use the optimization algorithm to suggest the architecture of our network. And the second is a more hybrid approach, where we start with the algorithm itself. And anytime we have a block that depends on the model, we replace just that block with a very simple shallow network. So these are kind of the two approaches that we've been looking at to combine model-based methods with deep learning. So let's look at the first approach, deep unfolding. This is an approach that was inspired by beautiful work dating over a decade ago of Gregor and LeCun. So their idea was to start with an optimization problem and unroll it or unfold it into a deep architecture. So we go back to the algorithm we've seen before. What we do is we write down a fixed number of steps of this algorithm, typically a small number, let's say 10 steps of the algorithm. And then these steps will typically depend on parameters of the model, which we may not know. So in the final step, we free those parameters, meaning the parameters that depend on the model, we actually learn from data. So we end up with an architecture that follows from our underlying optimization algorithm, but it's learned from data, or the parameters are learned from data. And those of you interested in this approach, we have a recent review. We wrote about this approach in the Signal Processing magazine. So in the original paper of Gregor and LeCun, they looked at the sparse recovery problem. So a linear measurement model where our data is modeled as a linear matrix times an unknown sparse vector in Gaussian noise. And then the standard approach to this problem is to look for the vector x that minimizes a least squares error plus an L1 regularizer for x. And if you just use, your standard gradient approach or proximal gradient approach to this problem, you'll get an iterative algorithm that does these two things. It takes a gradient step that we see over here, and then it takes a soft thresholding step, which basically follows from this L1 regularizer. So a standard iterative algorithm for this problem, the famous ISTA algorithm, would just do iterations on this block. To get a deep network from this, what you do is you take this block, you write it down a finite small number of times. So these networks are typically quite shallow, maybe 10 layers. And then you free these parameters so that these matrices, instead of being dependent on this underlying model matrix A, we're now going to learn it from data. And in this way, we get an interpretable method that doesn't rely on a lot of parameters and could learn from small amounts of data. Now, the nice thing is that once we describe this in this optimization framework, we can use various extensions of optimization to get very nicely extensions of deep networks. So, for example, if we want to get a robust network that is less sensitive to misfits between the training and the test time, we could take a robust optimization algorithm. So we can add a perturbation to the model matrix. And if we just solve this as a robust optimization problem, we end up getting a very similar problem to what we've seen before, but we have this additional normalization. And this is not just an arbitrary normalization, it follows from the underlying optimization algorithm. But now we could unfold this robust formulation, and we automatically will get a robust network, which we can show, in fact, in simulations, that when there's a mismatch between the training set and the test set, then it actually behaves in a much more robust fashion than other standard approaches to this problem that train on much more data and are much more complicated. So we can use, all the machinery we have for optimization now and apply it to develop various different types of interesting new networks. So that was kind of the optimization framework. We can also use a plug-in approach for problems that are not immediately following from an optimization formulation. And we've used this approach a lot, for example, in communication networks, where we have many good heuristics, we have many good solutions. They're not necessarily directly linked to an underlying optimization problem. And in this case, we actually start from the good solution, the good algorithm. And instead of replacing it entirely by an end-to-end network, we only replace individual blocks that depends on parameters that we don't know with a localized shallow network. So just as a quick example, we've used this, for example, for simple detection, where here the popular approach is to use a Viterbi algorithm, which is basically a dynamic programming approach. And what we do is we keep the whole Viterbi structure, since it's very powerful, and we only replace the likelihood computation with a very shallow network that computes likelihoods rather than replacing the whole network in an end-to-end fashion. So this is the main idea, and I want to take the next 6 or 7 minutes that I have to show some applications. So the first application that we looked at was to standard image deblurring. So assume that we have a blurred image with an unknown blurring kernel and some random noise. And of course, there's been many, many, many approaches to this problem, both in the optimization framework and in the deep learning framework. But what we wanted to see is whether we can use this very simple systematic approach to get a competitive solution. And what we did is we just used a simple optimization algorithm where we seek features of the image that are convolved with the unknown blur. And we have a regularizer on the feature and a regularizer on the unknown kernel. And then we just unfold this using a very simple ADMM approach. And the nice thing is that it leads to a very powerful deep network, which is actually quite shallow. So it only has 10 layers. And we see that it actually competes very nicely. And in fact, it gives sharper images than many competing approaches that train on larger data sets and are much more complicated. Now, here, of course, we assume that we have a fixed regularizer. So we use, for example, an L1 regularizer. There's many problems that are much more complicated, and we may not have such a simple regularizer. So we took this one step further, and this is work that we did together with Professor Ruud van Sloan and Daniel Friedman from Google, where we also wanted to learn the regularizer in an unfolding fashion. So what we did is we assumed a normalizing flow distribution for the regularizer, but rather than learning the distribution in advance, that is done typically like in GAN networks, we actually unfolded the process of learning the regularizer together with unfolding the network. So again, we end up with a very simple network with a small number of layers, which could perform really, really well and better than competing approaches in much more complicated problems. So here we see images that are corrupted with very heavy noise, or we're missing areas in the image, and we can get very nice recovery even though we're using a very simple principled interpretable network. We could use this for many other problems. So anything that we can describe as an optimization problem. So for example, we've used this for signal separation. So in ultrasound imaging, for example, a very important problem is that we get very strong reflections from the tissue, which don't allow us to see the blood flow when we're actually interested in the blood flow. So in this case, we modeled the problem as a low rank plus sparse problem, where we assume that the tissue clutter is low rank and the blood flow is sparse. And then we used an optimization formulation that was unfolded into a deep network to do this separation. So those of you interested in these types of applications, we have a review on deep learning and ultrasound where we go into much more detail. So the idea is very similar to before. We have a least squares problem. We add a regularizer on the low rank part, a regularizer on the sparse part, and then we unfold it using proximal gradient descent. And this leads again to a very simple unfolded network that we use only 10 layers of, and it gives very good separation between the background tissue and the actual blood flow. We've used this for many other areas in ultrasound. So for example, we've used this to develop a very compact, efficient probe where we could acquire data in a very, very efficient way. And therefore, instead of having a big ultrasound machine, we can now do all of the acquisition within the probe, again, by using this model-based deep learning approach and get very good recovery, even though we're using a very simple probe. So here we see that we could get images that have better contrast and better resolution than standard imaging, again, by adapting the weights in this model-based fashion. And the nice thing, again, is that it trains on very, very small data sets. The last thing I want to show in ultrasound in this context is that we can use this even to get quantitative imaging. So not only to get better images, but actually to get quantitative information out of the ultrasound. And here what we did is we modeled the wave propagation, which typically leads to very complicated equations. But using this model-based framework, we could learn the parameters in these wave propagations and actually get quantitative information. So for example, we could get speed of sound from the ultrasound data, and that automatically indicates area, for example, of tumors where the speed of sound is different. So together with a better image, we also get quantitative information, and our network is a very simple feed-forward network that is implementing these wave equations. We've used this for other problems in imaging in healthcare in general. So we've used this, for example, for COVID detection for both X-ray and ultrasound. So let me take another 2 minutes to quickly just end by showing how we could use this for super resolution in both microscopy and ultrasound. So in microscopy, one of the fundamental challenges is that we can't see beyond the diffraction limit. So we can't see details that are smaller than half the wavelength used for illumination. So in 2014, the Nobel Prize in Chemistry went to this very, very clever idea of fluorescent imaging, where basically we introduce fluorophores, and then we control their fluorescence so that instead of taking one image, we take a series of images, where in each image, we make sure that only a small number of fluorophores are actually fluorescing. And in that way, we could take thousands of images, pinpoint the fluorophores, and get super resolution by summing them up. So what we're actually doing is that we're getting spatial resolution at the expense of time resolution. And what we wanted to look at is whether we could get good spatial resolution, but not have to have so many time samples. And we did that by increasing the density in the fluorophores, and again, using these model-based approaches to recover the underlying information. And here, the model that we use is the acquisition process and the fact that the underlying data is sparse. So we see that this could lead to very good spatial resolution, better spatial resolution than we had in the underlying images, but using 2 orders of magnitude less images. And this actually paves the way to live cell imaging. So together with Professor Gilad Haran at Weizmann, we started using these techniques for the first time for live cell imaging, and we're able to see cellular dynamics, for example, during T cell activation, that you couldn't see before because you weren't able to get this time resolution. And just to end, we're now using the same ideas in ultrasound. So, of course, in ultrasound, you can't inject fluorophores, but instead we inject microbubbles, which are FDA approved. So we inject these into the bloodstream. And then just like in fluorescent microscopy, we use these model-based learning methods to follow these fluorophores and be able to get good depiction of the blood vessels. So this is a recent study we did in Beilinson Hospital with Dr. Ahuva Grubstein and her team. And we scanned 21 patients with different breast lesions. And if you look over here, you see the original ultrasound images where all you can see are these black holes. So you can't see the details within these lesions, and therefore you can't detect whether they're benign or malignant. But after our model-based method, which was not pre-trained, so this is all done from the data itself, there was no pre-training here, we can see the details of the vasculature, which are markedly different in these 3 lesions. And from looking at this vasculature, the doctors were able to determine that this was a benign tumor, this was the cyst, you could see the fluids inside, and this unfortunately was a malignant tumor. So to end, we see that we could very nicely merge, traditional model-based signal processing algorithms with the power of machine learning. And this gives us interpretable methods from very small training sets. It allows incorporation of various different domain knowledge. And we could also prove some nice analytical results, which I didn't go into here today, that show the robustness and generalization abilities of these methods. So thank you very much for your attention. Those of you who are interested, we have a recent review where we go into more details of these approaches. Of course, none of this would be possible without the amazing teams of students and employees that I have the pleasure and honor to work with, and the amazing collaborators that we've worked with. So I'd like to thank them all as well. And thank you very much for your attention.
Thank you, Yonina. We have time for just one quick question. If sparsity is required, why are you using L1 regularization and not L0?
Okay, so yeah, thank you for that question. So just a few comments. First of all, these methods are not necessarily based on sparsity. So sparsity was in the original methods of Gregor and LeCun. They were based on sparsity, and we've generalized these to many other priors. So it doesn't necessarily have to be sparsity. But going back to that question of sparsity, we could, of course, unfold any optimization method. So, we could look at a greedy approach based on L0, and we've done that as well. L0 just is not as nice from an optimization perspective. So typically when people look at optimization techniques, they want to use norms that are convex and smooth and easy to work with. So that's why people use L1. But it's a very good question. And the nice thing is we could use these methods with L0 optimization, or in fact, any regularizer that we would like.